Next example is just the polynomial function. Also is a polynomial function, and we will apply the forward backward difference with error of OH and central difference with error of OH square to estimate the first derivative. Okay, by using the S in different value. First one, S is equal to 0.5. Second one, S is equal to 0.25. Okay, so we know that if we take the first derivative of the function, we get the exact one like this, and we finding the true value. This is the exact solution. We call this the exact solution because we derive it analytically, and we have the formula, and after we substitute the value of h equal to 0.5, we get this. Okay, this is the exact solution. Okay, if we apply the forward difference, by using h equal to 0.5, okay, we apply these two values, substitute into this function. So you see that for the forward difference, we get the value of this, which h equal to 0.5. That is not small, right? This is not small enough. It's maybe not small enough. You see that the error is just very close to 60%. That's cannot acceptable, right? The error is a lot. It's about 60% error. And by using the backward difference, you see that for the backward, we do the same thing, but we use the backward value instead, and we found that the error is fall to close to 40%. It's not acceptable also, right? Okay. But if we use the central difference, the error is become 9.6%. Okay, it's better, but actually we cannot accept it because it's maybe 10% error. That is not good for us. So because of we used s just only 0.5, it's maybe not small enough. So if we do it again by using s equal to 0.25, so what does it mean? It means that xi is equal to what? Xi is represented by xi plus h. This is xi plus 1. This is 0.5 plus 0.25. It's become 0.75. So we get this value and also this value. Okay, so according to this, you see that for the forward difference, the error is falling to 26.5%. From what? From approximately 58.9. 58.9% is for h equal to 0.5, right? And this h is equal to 0.25. Okay, so you see that this can be explained the truncation error of OH. So according to this, you see that when h reduced to h equal to 0.25, so that means the error is reduced linearly, same as h, right? Approximate linearly. So you will see that the error from 78.9 reduced a half, very close to a half of the error when we apply h equal to 0.5, right? In the same manner of backward difference is reduced to approximately 40%, if I remember that, okay? It's reduced to 21%, 21.7%. So it is in the same manner of the value of h that is reduced to h equal to 0.25. Okay, this is in the same order because it's reduced with the a half of h. And if we apply for the central difference, we will see that the error is reduced to 2.4%, 2.4%. From what? From approximately 10%, right? With h equal to what? 0.5. But now h is equal to 0.25. It's reduced to a half. Okay, it's reduced to a half. But we know that the central difference, the error is with the order of OH square, right? So if we reduce it to a half, so the error is maybe approximately reduced with a half square. It's 1/4, right? So the 10%, the error of 10% should be reduced to be 2.4%. Okay, approximately 1/4 of the error of the O error. Okay, do you understand for the term of OS and OS square? Okay, so that is can we indicate that the order of the error is in which value? Okay, so we can predict the error by using the value of h. Okay, so it means that if you reduce the size of h, just the linear value, okay, so the error of the forward and backward, it just should be reduced in the same order. But in the central difference is decreased with the second order. Okay, so that's all for the finite difference. Okay, so if we apply for the high accuracy differentiation formula in the same manner, if we use the same example, if we use the same function with h equal to 0.5 and also h equal to 0.25. If we use to estimate by using the forward, backward, and central, if we use the simple formula, we will obtain the result as shown in this table. But if we apply the high accuracy differentiation formula, so that means that for the first forward difference, for the first derivative forward difference, we require two forward value, and for backward we also require two backward value. Okay, according to this, if we apply the high accuracy with the approximation of h equal to 0.25 also, but with high accuracy, so what's happened? It found that with high accuracy, you see that the error is falling down. And for the forward and backward, it's become 5 to 5.82 and 3.7% respectively. And for the central difference, it's close to 0. Okay, so it's better than the simple one. But we have to apply more value of x. We need more data. We need more data to approximate the derivative. Okay, that is maybe the shortcoming for some example. For some example, it's maybe not the data a lot like this. Okay, but if you have a lot of data, that is okay. You will understand better if we move to the topic of boundary value problem. You will see that if you apply high accuracy differentiation formula, high accuracy differentiation formula, you will have more unknown. The unknown will have, for this example, if you apply for the central difference, you will have at least 5 unknown to approximate. Okay, you have 5 unknown. So, but if you use just only simple formula, you will have just only 3 unknown. So the system of the equation is maybe reduced a lot. Okay, so for the simple application, the high accuracy formula is maybe not applied for the simple one. Okay, but if you would like to approximate some problem, is you require more accuracy, so it's have to, but you have to solve the big system of equation. Okay, so for this topic, do you have any question? It's very easy, right? If you do not have question, I will break this session and we will come back with the class activity.